Welcome everyone. I hope you're enjoying this online edition of CPPP conference. I hope you had an excellent French-themed lunch. I know I did have some very soft cheese. So let's try to regroup right after lunch for some of us and try to concentrate on some more C++. So just a few words about me. For those of you who don't know me, I've been working with C++ for almost 20 years now, and I worked for more years than I would like to admit on Advanced Installer. I think over 16 years now. And in more recent years, I focused a bit on developing an open source suite of tools that we call Clang Power Tools to help leverage the power of the Clang and LLVM tools infrastructure for Visual Studio projects and basically bring these tools in Windows land way before Visual Studio had any built-in support for that. Just a bit of logistics for today's presentation. I will try to keep an eye on the Q&A tab in Zoom. So if you do have questions, feel free to post them there. And if I find a natural stopping point during the presentation, I'll try to address them in context where possible. If not, I'll defer the questions to the end. And of course, I invite you all to join me on Discord for the dedicated chat channel for this presentation, or maybe in Salon numéro 2, where we can continue this conversation live off recording. So do feel free to reach out to me on Discord, at me, or on Twitter. If you have follow-up questions, my DMs are open as always. So going back to the talk title, the talk title should be taken very literally. It's not about goals for better code. It's not about best practices or code smells or writing exceptionally good C++. It's about what happens when we write code and we have to think about edge cases, edge situations, and unexpected things. Because we usually focus all our attention on the happy paths, and we usually test for those scenarios. Hopefully we write good tests for that. But we don't tend to focus very much on what happens on the unhappy paths or the error handling flow. And there are plenty of exciting things happening there too, not just in terms of making our applications or services more robust, but in terms of what envelops when such situations do occur and such events do fire up, and really understanding what happens behind the scenes when this error handling flow is unraveling. So, although not universally loved, exceptions are a powerful mechanism to maneuver execution on the unhappy path. Yeah, it's not the only way, but it's a very powerful mechanism. And there are exceptions everywhere, and in most situations, hidden or disguised in various ways, as we're going to see. So they're not always explicit or in your face. And I think some people are afraid of exceptions because they don't understand very well what's going on behind the scenes. And although they come with runtime performance costs, both in terms of runtime execution and binary payload in the binary, I think there's more myths and misconceptions about what's going on behind the scenes, and a better understanding of what's going on and how they're implemented would alleviate some of the issues and discussions that go along with embracing exceptions. So first of all, this talk is not about error handling strategies. It's not about exceptions versus error codes or structures such as expected of T, or about writing exception safe code or best practices in terms of how to do proper error handling in our applications. There are plenty of good talks about that. But let's not get ahead of ourselves. I think I would like to start this discussion with a story that will take place somewhere in the future, hopefully in 2023, hopefully a pandemic-free year. And the story starts a bit earlier. The story actually starts in 2018 with a proposal to add a stack trace library to standard C++. Very much inspired by Boost stack trace, if you're familiar with that one. Unfortunately, this proposal nearly made it in 20, but didn't for various reasons, like bike shedding on the names. But I'm happy to report that it will be part of C++ 23 for sure. It was actually the first library feature to be voted in. And I think the teaser there in the tweet is that we want to see a connection between standard exception and the stack trace library. We want to hook into when an exception occurs and log a stack trace or do something with the stack trace to get the contextual information from that exception. And among the key features desired and designed into this library feature would be a description function that should return a demangled function signature to be able to reason about a stack trace entry or a frame. A way to serialize a stack trace. So we should be able to query information from debug symbols, export tables, and other resources to return demangled signatures and location information. We should be able to reason about inline functions if we're talking about optimized release code. And of course, we want to avoid any overhead if possible when using such facilities. So the paid cost for using such library facility should be minimal. And the heavy lifting occurs starting from this static function current. Rough description of its implementation: a stack trace ng or stack frame. Of course, we will use a native handle just as we do with standard threads, and it should expose description information for the function, the mangle name, and the location information like file and line number. And a stack trace will be basically a vector of such frames or such stack trace entries, and the means to traverse them, exposed through the now familiar iterator interface. So you can traverse them as a range with begin end. Like I said, everything happens starting from the static function current, which has a few overloads. And all this information is stored in the frames within the vector with stack trace entries, and it can be traversed, consumed. So for convenience, there are several serialization utilities like toString that takes an entry or a whole stack trace, and you can mix and match depending on how much control you desire on the formatting of such a stack trace. For example, you may choose to traverse the stack trace that you get from this current static function. You may choose to traverse it manually and build and format the serialization any way you like using the helper functions from the frame. Or you can choose to serialize the whole frame as the implementation sees fit. Or there's even a output stream overload for that. Or you can choose to serialize the whole trace in whatever format the implementation decides to default to. So it's up to you to manage the control over how much detailed formatting you want there. And it really can't get any simpler than that in terms of consuming it. And I can't wait to see early implementations from our toolchain providers and to see how they land on various very different implementations underneath on different platforms that they need to support. And we're coming back to the focus of our today's presentation, and that is about how it's constructed and what's going on behind the scenes and what does it mean to throw a C++ exception or to catch it, or how things are constructed underneath and the platform specific implementation details that we need to understand. And to be honest, it kind of more looks like this than the other schematic. So it's not that pretty. It's kind of a mess in terms of being heavily tied to the operating specific details and intrinsic functionality. It's heavily tied to the C runtime that you're using. So we're going to focus about understanding the structure and the components involved and how they work together to build up an exception, and how they work together to orchestrate the workflow when an exception occurs and appropriate handler is searched and the unwind happens. So we're going to examine all these details. So this presentation is basically all about the exception internals. And I'm going to focus, because I have to choose, I'm going to focus on the Windows implementation. And we're going to see differences in terms of instruction set architecture. We're going to see a bit of differences between 32-bit, 64-bit, and ARM. And we have to start by addressing the elephant in the room, and that would be structured exception handling. And this is required because if you want to understand C++ exceptions on Windows, you really need to understand structured exceptions, because C++ exceptions are built on top of the structured exception handling machinery. By the way, on many slides, I have useful links related to the information I'm presenting. So feel free to follow those links when you get the slides later to read more about a particular API or functionality if you're interested. So just in case not everyone is familiar with this, you can enable asynchronous exceptions or structured exception handling from the Visual Studio property sheets or from the MS build configuration file. The async option or the /eha flags, compiler flags, are doing the same thing. And again, if these look a little bit alien to you, don't worry. You'll get yourself familiar with these concepts fairly quickly. It's not very complicated, but it looks strange. So a little bit of contextual explanation is needed. So the underscore try, underscore except keywords, they're not to be confused with the C++ equivalents. Actually, these precede the C++ exception specifications in the standard by quite a few years. So, but they conceptually try to accomplish the same things. Only you have more control over what happens when using structured exceptions, of course. And we're going to see what the exception filter is and how we can use it in the except handler. But let's start with the beginning. So life happens and applications do crash. So in this case, we have an example of a stack trace from an access violation exception. And let's see what happens when such an event occurs. Let's say we have a very silly example there, write through a null pointer, which of course it would be undefined behavior. But as in all things happening, you do have some behavior. It's not actually undefined. It's very defined what happens. It's just you shouldn't count on what happens. But the behavior is very well defined. The operating system fires up an interrupt handler there. And the operating system has a facility that you can hook into and gives you an opportunity to inspect the situation and react. So instead of the CPU melting just because undefined behavior happened, or let's say an access violation could be a dangling pointer as well, the operating system there gives us, through this structured exception handling mechanism, gives us the ability to hook into this event when this interrupt is fired, and instead of taking down the whole process, it gives you a way to inspect the situation, to log it maybe, or even try to recover it if possible. So let's start with what happens. First of all, the operating system gives us a convenient way of inspecting the situation by providing us with a snapshot of the current execution context. And by current execution context, I mean what the CPU was doing when this event occurred. This includes all the state registers of the CPU and various information about the memory when the operation was halted by this event, by this interrupt. So the context contains processor-specific register data, of course. So this is specific to the architecture. There are differences there, of course. And if we zoom in a little bit, we see the familiar registers there and other bits and flags that we're gonna see if they're relevant. More documentation, again, links on the slides if you want to drill down more. So let's see how we can use this exception context. And it all starts with a very simple structure, the exception record structure, which by the looks of it kind of hints like a linked list there. We have an exception code, exception flags, record link there, and some other parameters that are specific to each exception code that we're dealing with, because we have various kinds of exceptions that can be happening. And the payload information there in the exception record tends to be specific to each kind of exception. There are some differences there. If we analyze the differences between the 32-bit and 64-bit implementations, slight difference there. I will mention that the implementation on 32-bit uses a linked list structure of such records, whereas on 64-bit we have a lookup table, hash of some sort, to optimize this lookup process. So that's why the implementations on 64-bit are much more optimal in terms of how they look for handlers and how they handle the exceptions when they occur. I will try to point out the differences when there are some differences in terms of architecture for the implementation. Okay, so let's start with a simple example. Let's try to populate such a structure, the exception record. Let's say we have an access violation and it has a very specific code that you see there in the comments. We're not using the exception flags. We don't have a next exception in the chain. So, and we have to fill in the instruction where the exception halted, so the program counter, and some additional payload about the event. So now we're playing the role of the runtime or the operating system in filling out this structure, just so that we get an understanding of what's going on. Let's say we have a write fault, because for an access violation, we can have a read, write, or a data execution prevention fault. And in the payload there, in the exception information, we can additionally encode the virtual address where the write operation failed. So the memory address where the write failed, let's say a dangling pointer that points to some zombie memory. And to see how things are bubbling up in the operating system and the runtime, we have to understand that things start from this kernel structure, which is the thread information block. Don't be fooled about the Win32 there. Win32 is just a legacy terminology that just refers to the persona of the operating system. It has nothing to do with the architecture. So Win32 APIs also apply to 32-bit, to 64-bit APIs as well. So we have the thread information block structure, and it can be easily accessed in some ways, either by calling the kernel function ntcurrent tab, which actually gives us a pointer to this structure, and it's for the current thread, of course. Or we can access it through the FS segment register on 32-bit Windows, FS 18H there, or the GS register on 64-bit Windows. So GS 30H to be more precise. So I've listed here both methods. We can easily get a pointer to this structure by directly reading those registers or by calling this kernel function. So this TIB structure contains thread-specific exception handling chains. So and the pointer to the TLS. Yes, the thread local storage is also stored in this thread information block. So if you're curious about thread local storage and how that works, your investigations should start here as well. But going back to the structured information, structured exception handling information. So the exception lookup chain actually starts in this TIB structure, and this is where we get the structured exception handling frame, and this is where we start, or rather the operating system starts the lookup to find an exception filter appropriate for the event that occurred. So this is how the operating system knows how to start and traverse such a structure that we're building, or the compiler rather is building for us. Just to mention that again, there is a difference here on 64-bit within Windows. For stack unwinding, the implementation is done in kernel mode instead, and it's much more optimized. So you don't pay such a big runtime cost when an exception actually occurs on 64-bit. But for simplicity, we're going to analyze a simple chain, so the 32-bit model, just to get a feel for how this lookup mechanism works. It's a bit more convoluted on 64-bit, and that's why I chose to depict diagrams for 32-bit. So we have an exception registration record, which has the next record and a disposition handler, our callback basically. So this is a way we can chain up such records, and we start from the TIB there, and we get the first record, and then we follow this linked list all the way through until we hit a handler that accepts this event. And these candidates that we have in the chain, my handler 1, handler 2, handler 3, are just plain functions with a specific signature where we get called up on, and we can decide by inspecting the context information if we choose to continue execution or search for another handler down the chain. So this is how the event occurs and bubbles up through our code to look up for appropriate handler. And we're going to see a concrete example of this. Of course, if you don't register any handler and a structure exception occurs, your process is going to crash. And I'm going to show this towards the end, what happens in case no such handler is installed, and what can we do to handle these situations where exceptions are not handled. But the default implementation is the process crashes, which is a good thing, because you don't want a process limp along when such event occurs. It could do more damage by letting it survive. So we get a very simple example here. We get the thread information block, and we construct an exception registration record. We set up a handler function that we're going to define, and we link it up in the list. So we set this record to be at the head of the TIB exception list. So we link it up there, and the important bit there in the yellow background is where we try to fire up such an event to see what happens, and to see if our exception handler there in blue over here will actually be called, and what can we do about it. So the required signature for such a handler would take an exception record, a structure that we are already familiar with, a frame, the context structure that we've seen with the CPU state, and some other parameters. And from the exception record, we can extract lots of information there. We're going to see more details later, like the exception address, exception code. And if we choose not to handle this exception, so this filter decides this particular event is not for consuming here, or we can return exception continuous search. So look for the next handler in the list. In case we do have a magic fix, there are reasonable situations where you can actually use this mechanism to orchestrate access to memory. And I'm going to show a very simple example, but realistic example. If you do have a magic fix for this event, you can return exception continue execution, and that will instruct the operating system to resume execution from the saved program counter, from the exact location where the event occurred. So it will basically continue, it will resume from where it halted. Presumably, the stuff we did here in the yellow box makes it so that the exception doesn't happen again. Let's see what else can we extract from this information, from this exception record. we have here a very simple example of an access violation. And in case we have an access violation, we can see the operation type that happened. And this is in the exception information record. I told you about the exception information record contains very specific information based on the exception code. So each kind of event or each kind of structured exception can carry specific payloads in this structure. For an access violation, on the index 0 there, we have the operation type, and that will tell us if it's read or write. And from the exception information record at index 1, we get the virtual address to see where the fault occurred, because we have an access violation and we want to see what piece of memory was touched there. So from this, combining this information, we can decode to see if we had read a bad pointer, or write through a bad pointer, or read through a null pointer, or write through a null pointer. So we can decode what really happened there in this access violation scenario, and attempt to log it, or attempt to fix it, or anything. And we can instruct the operating system to continue execution. And that will stop searching for another handler, such as this one, and it will resume from the instruction where it halted. But it's really too much boilerplate for such a simple handler that we wrote there. And of course, the compiler can help there, using these magic keywords with double underbar in front. Underbar try and underbar except, we can accomplish the same thing, only the compiler will generate these exception records and chain them appropriately and stack them together to register this information, so that the operating system can look up for our handlers as we desire to orchestrate this process. So same thing as before. But instead of defining our exception records, we actually use the keywords, and we defined an exception filter function, which has a particular signature. And we have a helper function, which gives us the exception information. And we're going to see what structure is behind that. And if we decide to, this exception filter will pick up this type of event, then we will continue execution. And if this exception filter is not it's not supposed to handle this event, then it will instruct the OS to continue search for another handler. So get exception information, this function here highlighted in here, retrieves a computer independent description of an exception and information about the computer state, basically those context structures, and information about the thread where the exception occurred. So this function can only be called from a filter exception, so only from an except handler. It doesn't do anything if it's called outside of an except handler. And it returns this exception pointer structure. So this is a new structure we're seeing. And of course, we can also get the exception code. I've put here more links for you to drill down. So this new structure that is returned by get exception information is the exception pointer structure. And it basically combines the two pieces of information that we've seen right from the start. We've already seen the context structure with the CPU state and the exception record, which describes the particular instance of this event that happened. Again, structures that we're familiar with by now. And we're going to see more examples in the later slides. And so this would be what get the exception information returns. What about the exception filter? So how does that look like? So the exception filter, of course, receives as input the exception pointers returned by the other API, and it can decode the information inside, like we've seen already. Here, I'm going to show a more realistic example. Let's say we're interested only in an access violation event and only an access violation through a write fault. So right from the start, we're filtering out. So we're saying if it's not an access violation through a write fault, then continue search for another filter. This is not what we're supposed to do. But in case it was an access violation through a write fault, then we can decode the memory address, the write address, because a write was attempted. You know, again, from the payload information, we can extract the write address, and we can choose to unprotect that particular page, that write address, and continue execution. So a plausible scenario here is implementing some kind of a heap structure where you want to fold in memory as soon as it's touched. So you want to reserve memory, but you don't want to commit it right from the start. So a particular useful scenario is folding in pages as they're touched. So as soon as you a write operation is attempted at a particular address from a reserved range, then you can then such an access violation as a write fault actually occurs, and you can see, oh, this address is within my reserved pool of pages, and I can choose to write my initial state of is that those memory pages are write protected, and when this fault occurs, I can write unprotect that particular page where the write occurred, and instruct the operating system to try again. So it will continue execution. So basically, it will resume execution from the faulting instruction as if nothing happened. And the second time around, when that write operation is attempted, now that page is unprotected, and you can actually write to it. So this is a way of managing reserved pools of memory pages that are write protected, and they are faulted in on particular policies on demand when they're first written to. So this is a valid strategy to do that. And of course, you can use structured exceptions to do that. And it's a very efficient mechanism to orchestrate that. I talk about the misconception that exceptions or exception handling means performance overhead or means slowing down the process. These mechanisms of using structured exception handling are highly efficient. These are very optimized operating system internals. Many of these primitives implement in the kernel, and they're very efficient in handling such scenarios. So this is a valid, realistic use case for handling access to memory pools. So why are we bothering to understand this aside from very exotic scenarios, like, for example, if we're trying to build a garbage collector or something like that, or a memory pool, a very smart memory pool. Aside from those corners scenarios that might not be for everyone, certainly they're not frequent in use, we really should understand what's going on behind the scenes, because C++ exceptions, and that was my promise right from the start. I promised you that you're going to have a better understanding of what's going on, and you're going to fear exceptions less. If you understand how C++ exceptions are built on top of this very same SEH machinery, and how the compiler does all the bookkeeping work, then maybe we're not going to be so afraid of C++ exceptions, and we're going to judge them on their value when they're appropriate, of course. I'm sure some of these identifiers should feel familiar to you if you've spent enough time debugging in Visual Studio. So for sure, you've seen APIs like raise exception or those mysterious CXX frame handler or accept handler 3. I bet you've seen that in stack traces when breaking on some debug breakpoints while investigating something. So this would be a fairly realistic mapping of how concepts from the C++ world map to the structured exception handling universe. So a throw statement in C++ is basically translated to a raise exception call. Try catch are handled roughly through the try except mechanism that we've seen already with the exception filters there. Local variable destruction is handled via try finally blocks. I don't have time to go into details on how finally works, but I've linked some material there in the slides where you can see more examples. And the CXX frame handler maps to the accept handler 3 there. Let's see what happens. First of all, if we talk about C++, we talk about custom types, we talk about destructors, and we have to think about destructors and type hierarchies because they're relevant in the unwind process and because the relations between types are relevant in the catch handlers, because you can catch exceptions behave polymorphically. So you can catch related types. So that's why the compiler needs to build up information, and it has all that information about how types are related to each other. And when building up these exceptions, it has to have a clear view of this type information. So I've listed here some of the structures, and I won't go into details because the details are fairly gnarly and highly proprietary to how the compiler works and generates those. But I'll just say that it needs to build the required information in the function prologues. So all functions that are assumed to be asynchronous, where such exceptions occur, will have a required prologue that is generated and epilogue that is generated with this information in case such an event occurs within that function's stack frame, so that the compiler knows which handlers are involved and what types need to be involved in the unwind process, what objects were already constructed, what needs to be destroyed, and so on. But I won't spend much time into that. Let's see how we construct such an exception. So we have the CXX throw exception function, and a fairly simplified view of that function would look something like this. Very similar to what we've built by hand in the very first slides. We build up an exception record, we fill in the code. In this situation, we have the exception number, which is just a magic number there. You can actually see the value is actually MSC encoded there. And we mark the exception as non-continuable, so it needs to be handled. And we have the payload information. We have some magic numbers there. We have the important bit, which is the exception object. So this is the address of the object that was thrown, our C++ object. We see here an opaque signature, but this is our object. And the type information is stored separately. So throw information, this throw structure is filled in by the compiler, and it contains information about the type that is thrown here. And it just calls the raise exception function with all these fields. So basically, that's how a C++ exception is born. Let's flip this around a bit. Let's see if we can map a structured exception to a C++ exception, where there is a way to do that. The CRT gives us an API. It's called setScTranslator, and it gives us a way to handle structured exceptions as C++ typed exceptions. And it's very, I forgot to mention, you have to install this translator on a per thread basis. Like we've seen, all the lookup chain for the exception filters happens starting from the thread information block. So you need to install such a translator for each thread that you spawn in the application. And this can be achieved fairly easily if you're building, if you're using a standard thread, for example. You can shim the construction of standard thread, for example, and have a shim procedure that you insert there before forwarding the arguments to the standard implementation. And you can have a handle SCH function that installs this translator before actually invoking the thread callback function, the thread before the thread actually runs. So this is how you would very easily shim a thread and install an SC translator right before invoking the function and forwarding its arguments there. And the function signature looks like this. You get the as input the structured exception code and the familiar by now exception pointer structure. And we can choose to decode and handle. I've listed here just a few of the possible exception structured exception types. There are many more. We see here some very basic examples. And I've chosen to highlight again the access violation type, where you can decode it as we've seen previously. So again, this slide is basically just a reminder. I've already shown this a couple of slides back. So in this translation function, again, we can extract from the exception pointer the same information and decode and choose to, let's say, log this information. In this situation, we see here a string serialization of some sort where we encode all this information about the event. And after we encode all this information, maybe we can even traverse and trace this information record and build up a stack trace. And we can package up all this information that we extracted from this event, this structured exception. We can package it up, including origin information, source line number file. And we can all neatly package this up in a structured exception object that we can throw as a C++ typed exception. So if you want to handle in our application and handle all such events uniformly, and we don't want to mess up and pollute our code with all sorts of __try __except and all that business, because that's ugly to handle. You can package up all these ugly bits into a translator function and never have to deal with structured exceptions explicitly in code. So you have this layer that maps all the structured exceptions into C++ exceptions. And except from this bubble where you handle the SCH stuff, everywhere else in code, you just deal with C++ exceptions. And you just have a particular type of C++ exception that encodes these types of events in case you want to log them or do something. So this is how you deal with an exception in flight, again, for a current thread. So like you might be familiar with current exception function from the standard library. Similarly, you can get the current execution context, and you can see what happened when an exception is in flight, when an exception occurred, and choose to log it or trace it or build a stack trace like we've seen at the very beginning. So we need to get a hold of that context structure that we've seen, that snapshot of the process CPU rather. So we've already seen this context structure. We've seen it in the translator function just now. We've seen it in the exception pointers earlier when we talked about the exception filters and get exception information. So we basically need to get a handle of this context record. How do we get the pointer to this p context? That's the problem at hand here. Just a bit of a warning, it's not pretty, but it works. A little bit of CRT magic and incantations there. This will be the recipe. By the way, the whole code is expanded here, but it's actually it works as is, so you can actually copy paste it. This applies for newer newer Visual Studio implementations, so newer CRTs. For really old stuff, if you're still stuck on that, like 2013, there's a slightly different implementation in the CRT. It's all based on undocumented structures and APIs, but it works and it's stable. These are the stuff that you need to include if you want to make it work. So it's what you see in the slide, it's complete. So it's nothing omitted there. Undocumented APIs, take it as it is without guarantees, but like any good C++ stuff, it's guaranteed to work for years. So it's never gonna break. But yeah, it's ugly. Fortunately, you can pack all these things in tightly into a separate file that you don't have to touch ever again, like we do. Worth mentioning here, per thread data. This would be a C rather structure from the CRT, where we have encoded all this information about the snapshot and the contextual information of the in-flight exception, or that gives us that context record that we so badly desire. Again, some differences here between the architectures, as you would expect, because we're talking about the process snapshot, the CPU state. But this all handles the situation where we want to retrieve a context structure for an in-flight exception. But what happens if we want the same thing, but outside of a context of an exception, like no exception occurred, no exception is in flight, we're not in a catch handler, nothing happened. Particular very practical examples would be to debug some issues. For example, you might want to build up a stack trace to investigate in a particular function. You want to investigate how you got to a particular point, or a particular function, or a particular point within a function, through which call stack that point was reached. Let's say you have multiple ways of reaching that function within the application, various scenarios and various call dependencies that you might end up in that very same function. And you want to trace all that information to log it and inspect patterns and discover patterns in which way a particular function is called. Maybe it crashed, maybe it didn't. Maybe you're just investigating to find out more about how a particular function is invoked, and you want to do that investigation outside of a debugger context, like a post-mortem investigation. And you can leave those breadcrumbs behind and have a way of building stack traces for particular points in particular functions without actually being any crashes, any access violations. So a way of logging and discovering what happened outside of stack fault. So how do we get a context in that situation? Because we don't have any exception in flight. Where there's an API for that. Actually, a kernel API, Rtl Capture Context, which gives us on demand the execution context of the CPU. So basically, we can get this context structure that we've seen already, and that was provided for us automatically as input to all those callbacks we've seen in the context of exceptions, pun intended. In this situation, we get it a la carte, we get it on demand anytime we want to. So anytime we call Rtl Capture Context, we get a snapshot of the CPU, and we can trace that particular point immediately. So the same facility that I've kept showing, but I've never shown the implementation. But the same facility here, the stack walker, trace from context that we've seen in all situations, like translator function, like the exception filter, and so on. The same facility can be used because it only required as input parameter, it only required such a context structure. So the same facility can be used to build a stack trace from any particular point in any particular function without the need for raising a structured exception. And we've seen this helper function time and time again on almost all slides, trace from context. It's a means to walk the stack, basically, and construct what we're going to get, something similar to what we're going to get in C++23. So if you want to exercise how that might be implemented, I'm showing here just a bits and pieces. It's not complete code here. Basically uses APIs such as stack walk from the debug help library provided by the Windows SDK to traverse those stack frames and build up exception information, stack frame information, and symbol decoding, and so on. So initializes stack frames, stack walks, and composes each frame by extracting information about the program counter and the offset, and decoding information about symbols in each stack frame, so each demanded function name, file name, file number, and so on. Again, you have to take into consideration address space layout randomization. So you have to do some pointer arithmetic there to be able to handle SLR. In order to translate addresses correctly, because each time the process is loaded at a different base address. Some bits and details there. Of course, there are some required architecture differences for 32-bit, 64-bit, and ARM. You have the sim from address API from the debug help library that you can use to demangle and decode symbols. I won't dwell too much on this because it's just it's nothing fancy. It's just mechanics and boilerplate that you need to write to make it work. And all the heavy lifting is done by this DLL from the Windows SDK that you can statically or dynamically link into your project and leverage its APIs. And the reason I'm not dwelling too much on this is because I've done another presentation where I focus exclusively on how we can build these stack frames and construct this information from the context structures and serialize it and how to deal with it. So I have the link here if you want to focus exclusively on how to build better stack traces and decode information later on and symbolicate them post-mortem and so on. I do encourage you to watch this other presentation. I did that C++ now. One more thing before we close up. How do we handle the unhandled? Because I mentioned earlier that the default behavior when we don't install any exception filter is that the CRT basically installs such a filter for us. So I'm not sure if you're aware, but the main function that we actually write in C++ is not actually the entry point in the module. There's a real entry point in the module, which is defined by the CRT. And inside there, it does a bunch of setup, among other things, sets up environment variables and globals and destructors for at exit and so on for statics and such things, and installs exception handlers for such unhandled scenarios, because basically before calling our main, it guards them. It guards our main between a try except handler, and it has less chance to do something before taking down the process. And the default behavior is basically to terminate. So this is what the CRT does. It sets the unhandled exception filter. And the default implementation of that filter is basically to terminate the process. And that's it. But we can intervene once more. And if we want to handle the unhandled, we can set an unhandled exception filter callback that we must define, and it will be called for us by the CRT. And when an exception occurs in a process that is not being debugged, because the debugger takes priority over this first chance exceptions, and the exception, if the exception is not caught by any other filter in the chain, either we forgot to catch it somewhere or no filter actually matched, either through STH or C++ typed exceptions that didn't match. So by any means, if that exception basically falls through, this is the last chance to catch it and do something about it. As opposed to the SCH translator function, which needs to be installed on a per thread basis, this needs to be installed just once per process. And the CRT will call our unhandled exception handler there that I've marked here in blue. Will call us when it doesn't find any handler and that exception basically fell through. And the unhandled exception signature is very familiar. Again, we've seen the exception pointer structure a few times now, and we can choose to do something. Basically, at this point, if everything fell through, the only reasonable situation, I think, it would be just to log this information for post-mortem investigation. So again, our familiar stack walker traces from context, retrieves the context record from the exception pointers parameter there, and just maybe chooses to present it or archive this information somewhere, log it somewhere. And the only reasonable thing is to continue execute handler. So the handle the unhandled is a last stop measure where you can archive all this information and make sure you have this information on hand for later investigation. And again, I'm going to refer you to the Quest for a Better Crash talk I did at C++ Now, where I show scenarios on how to use this archived information and how you can resymbolicate it post-mortem and investigate the core dumps and stack traces out of band by not being able to debug the process live. And you can basically rehydrate this archived information that you stacked away when such an event occurred. All right, that's about it. Do join me on Discord if you want to chat some more about this. If you have questions or want to discuss particular scenarios, real case scenarios of where these things might be useful.